Hello and welcome to this third presentation in our series related to torsion of circular cross sections. This presentation includes further exercises. In the first presentation we introduced the concept of simple torsion of circular shafts and derived the simple torsion equation. In the second presentation we applied the simple torsion equation to solve various practical problems related to three separate exercises. In this presentation we now consider three further exercises which are slightly more complicated due to the contextualization. It is assumed you've seen the previous presentations before reviewing the further exercises in this presentation. Presentation overview for the simple torsion theory related to the further exercises we'll now review. Here is the simple torsion equation we derived in the first presentation, and also the formulae for the second polar moment of area of a solid section and the polar second moment of area for a hollow section, as shown here. In this presentation we commence with exercise 4, where we have to calculate the power that can be transmitted, symbol P, for a given scenario. And note within the scenario there is a factor of safety to be applied to the ultimate shear strength. Exercise 5, we have to calculate the actual force applied, F, to the handle of a wrench, typical socket wrench, and also the angle of twist of the shaft of the wrench, theta. Exercise 6, we have to calculate the shear stress and the angle of twist, theta, given a torque diagram. This scenario considers three gears mounted on a shaft. From the information given we can calculate the various shear stresses in the shaft and also the angle of twist. The presentation ends with a series of questions for you to attempt at your own pace. And here are the approximate timings related to the commencement of the various sections within this presentation to hopefully aid your access through the presentation. Please note these are only approximate timings. Exercise 4. A jet engine compressor shaft has an external diameter of 28 mm and an internal diameter of 23 mm. If it rotates at 11,950 rpm, we're asked to calculate the maximum power that can be output by the shaft if the ultimate shear stress for the material is 580 meganewtons per meter squared, to which a factor of safety of 1.5 is to be applied. We have reviewed the application of factor of safety in previous calculations. We obviously have to apply the factor of safety of 1.5 here to the ultimate shear stress. I would encourage you to stop the presentation and attempt exercise 4. Extract the information very carefully from the question, but I will show the full work solution on the following slide. Exercise 4, solution. Just notice because the material ultimate shear strength is stated as 580 megapascals, the Pascal is a Newton per meter squared, then I'll convert all of my dimensions into meters. So the 28 millimeters at external diameter shown here, capital D, is 0.028 meters, and the internal diameter shown here of 23 millimeters, little d, is then stated in terms of meters, 0.023 meters. The angular velocity of 11,950 rpm, omega, is calculated in terms of radians per second. The ultimate shear strength, stated in the question, 580 times 10 to the 6 newtons per meter squared, to which we have to apply the factor of safety of 1.5. Calculating the maximum radius r, it's actually capital R in the diagram, that's the outside diameter, uppercase D, divided by 2. So it's 0.028 divided by 2, so 0.014 meters. Exercise 4, solution continued. So firstly I've calculated the working torsional shear stress, the permissible stress. So the working stress tau is equal to the maximum shear strength divided by the factor of safety. So inserting the values for the ultimate shear strength and for the factor of safety of 1.5, we can evaluate the working shear stress. That's 387.7 times 10 to the 6 newtons per meter squared. We can calculate next the polar second moment of area, the J value for a hollow section shaft shown here. Inserting the values for the outside diameter and inside diameter. We evaluate the polar second moment of area to be 0.03287 times 10 to the negative 6 meters to the 4. Next, from the simple torsion formula, I found the applied torque T. So from the question, I'm using these two parts of the simple torsion formula and rearranging for capital T. That becomes the permissible shear stress multiplied by the polar second moment of area J divided by the outside radius. Inserting the values, the torque applied is 910 Newton meters. Finally, the power transmitted P is equal to the torque multiplied by the angular velocity omega from our previous slide. The torque is calculated above, 910 Newton meters. The angular velocity calculated on the previous slide. That evaluates to a power of 1.139 megawatts. That's just 3 decimal places. Exercise 5. The steel shaft of a socket wrench, shown here in the sketch, has a diameter of 12.7 millimeters, labelled here, and is 460 millimeters long, stated here. If the allowable shear stress is 62 meganewtons per meter squared, we've got to calculate the maximum force, F, that can be applied to the wrench handle. Force F shown here on our sketch. Here's the wrench handle. If the handle is 250 millimeters long, labelled X in the diagram here. We're also asked to calculate through what angle will the shaft twist under the action of the maximum torque. The shear modulus G is stated as 81 giganewtons per meter squared. Notice for reference in the sketch here, there's a hint that torque T applied to the socket wrench and shown here is calculated from the formula F times X. The answers are shown in the bracket here. I would encourage you to stop the presentation and attempt this question, but the full solution to exercise 5 is shown on the following slides. Exercise 5, here's the solution. Notice that in the question, the allowable shear stress is stated as 62 meganewtons per meter squared. So tau here, 62 times 10 to the 6 newtons per meter squared, and the shear modulus G is stated as 81 giganewtons per meter squared. So shear modulus G here is 81 times 10 to the 9 newtons per meter squared. And so as these properties are stated in meters squared, I will ensure all the dimensions are now stated in meters. So although the diameter of the socket wrench in the question is stated as 12.7 millimeters, my capital D here for the outside diameter is 0.0127 meters. Notice that the length of the socket wrench, or the shaft, for our analysis purposes, is 460 millimeters long, so L is 0.46 meters. And the length of the wrench handle is 250 millimeters, and again, that dimension X in our diagram is 0.25 meters in our calculations. I've calculated the maximum radius for our formula. That will be the outside diameter divided by 2. So in this case, that's 0.00635 meters. So notice that's labelled as capital R in our diagram here. Exercise 5, solution continued. So part 1 here, we're calculating the second polar moment of area. The J value from our standard formula of pi d to the power 4 divided by 32. Inserting the value of the diameter from the previous slide in meters. That evaluates to 2.554 times 10 to the negative 9 meters to the 4. Next, from our simple torsion formula, we're going to calculate the maximum torque, that's capital T shown here, and given the information in the question, that will mean we will use the first two parts of the simple torsion formula. So transposing for T, that becomes the allowable shear stress multiplied by the J value from above, divided by the maximum radius calculated on the previous slide. Inserting the values, the maximum torque evaluates to 24.9 Newton meters. The question actually wants us to determine the maximum force that can be applied to the 250 millimeter long handle. So this force F labelled here. And we're informed in the question that the formula for torque is the force applied to the handle multiplied by dimension X, which is 250 millimeters shown here. Simply rearranging for the force F, that's the torque divided by dimension X. Inserting the torque from above and the dimension X from above, the maximum force is approximately equal to 100 newtons. Exercise 5, solution continued. Now we're asked to calculate the angle of twist from the simple torsion formula. So now I'll be using these two parts of our simple torsion formula, transposing for theta. So theta is equal to the shear stress multiplied by the length of the shaft or socket wrench divided by the shear modulus divided by the R. Inserting the values, the angle of twist is 0.0554 radians. And finally converting from radians to degrees using our standard formula here. It's approximately 3.2 degrees to 1 decimal place. Here's exercise 6. A 30 millimeter diameter solid steel shaft, shown in our sketch here, freely turns in bearings at the ends of the shaft labelled A, shown here, and E, shown here. The shaft is driven by gear wheel C, shown here, which applies a torque T2 of 450 Newton meters, here's torque T2, in the direction shown. Here's the arrow head of the torque vector. Gears B, shown here, and D, shown here, are driven by the shaft and have resisting torques T1, shown here, 275 Newton meters, and T3, shown here, of 175 Newton meters. Notice the directions of T1 and T3 shown here. They're opposite to that of torque T2. Lengths of shaft between B and C, labelled LBC, is 500 millimeters, shown here. And lengths of shaft C to D, LCD, is 400 millimeters, shown here. If the rigidity modulus is 80 giganewtons per meter squared, we're asked to calculate first of all the maximum shear stress induced in each part of the shaft. So that's in the shaft section B to C and then C to D. And also we're asked to calculate the angle of twist between gears B and D, shown above. The answers are shown in the bracket here. Exercise 6 continued. From the information given, we need to draw what's termed a torque diagram, shown here in Newton meters. This is slightly analogous to the shear force diagram that we often draw when considering shear forces applied to beams in bending. If you consider the torques here analogous to the shear forces, in a shear force diagram associated with beams, we account for the direction of the shear. We have a positive notation for shear defined, and we draw our shear forces from left to right across the beam in accordance with that notation. The same approach applies here, Essentially, we have a positive torque notation, which we will consider to be in T2's direction, which means that the direction of T1 and T3 in this case will be in a negative direction. So just as we draw a shear force diagram for point loads on a simply supported beam, we're going to draw the torque diagram for the various torques applied at the gear locations on our rotating shaft. So to our notation, on the left-hand end of our torque diagram, we have T1, which is in the negative sense, so drawn down here at negative 275 Newton meters. That's then a constant torque across section BC. And at gear C, we now have a positive torque applied, and we're given in the question that's 450 Newton meters. So we draw our torque at C in the positive sense here, upwards on our diagram. That's then a constant torque from C to D of 175 Newton meters. That's negative 275 Newton meters plus 450 Newton meters. And at gear D on our diagram, we now have another negative torque. It's negative 175 Newton meters. And that closes the diagram, as we would expect, and as would be the case on a shear force diagram. So now we know between shaft section B to C, we have a negative torque applied, negative 275 Newton meters. So we can work out the torsional shear stress for section BC and also the angle of twist for section BC. And we can then do the same for section C to D. We know the applied torque is 175 Newton meters between C and D. To get the overall angle of twist between B and D, we simply add the angle of twist BC to that of the angle of twist CD. So if you now think you can attempt exercise 6 without further assistance, I would encourage you to stop the presentation and do so, but I will show you the full work solutions on the following slides. Exercise 6, commencement of the solution here. To extract the information from the question, the shaft diameter was stated as 30 millimeters in the question, but I'm going to write the shaft diameter D in meters, because in this question the shear modulus is given in as 80 times 10 to the 9 newtons per meter squared, so I'm going to ensure all my dimensions are in meters to prevent any unit conflict. The applied torque given in the question, T2, here was 450 Newton meters. And then the resisting torque, T1, shown here, was 275 Newton meters, in the opposite sense to T2. And resisting torque, T3, shown here, was 175 Newton meters. The length of the shaft, LB, its length here, 500 millimeters, so that's 0.5 meters. And the length of the shaft, C to D, shown here, was 400 millimeters, so 0.4 meters. The maximum radius of the shaft, call it R here, to use in our simple torsion theory, is D divided by 2, so 0.015 meters in this case. Exercise 6, solution continued. So part 1, we're going to calculate the polar second moment of area, symbol J. For a solid shaft, we know that's pi d to the 4 divided by 32. Our diameter in this case is 0.03 meters. So that evaluates to 79.52 times 10 to the negative 9 meters to the 4. Next, we're going to calculate the maximum shear stress between portions B and C on the shaft. So this portion of the shaft. And to do that, we'll use these two parts of the torsion formula. So rearranging for the shear stress, so that's the torque between section BC multiplied by the radius of the shaft divided by the polar second moment of area. Inserting the values, the torsional shear stress between section BC is 51.9 times 10 to the 6 newtons per meter squared, or approximately 52 meganewtons per meter squared. If we now consider the maximum torsional shear stress between portion CD of our shaft, So this section here is exactly the same approach as for part 2 above. The only thing that's different here is that torque TC is used of 175 Newton meters. So the torsional shear stress between section CD is 33 times 10 to the 6 Newton per meter squared, or of course that's 33 meganewtons per meter squared. Exercise 6, a solution continued here. Step 4 here, we're going to calculate the angle of twist between portion BC of our shaft. So again, this section here. This time, from our simple torsion formula, we'll use this part and this part of the formula. So rearranging the equation for angle theta between portion BC, we basically multiply by L and divide by G. So that's going to be T multiplied by L divided by G, J. Inserting the values, our torque is negative 275 Newton meters from our torque diagram here. The length of shaft B to C is 0.5 meters. The G is given in the question, and we calculated the J on the previous slide. Evaluating the angle of twist between BC of our shaft is negative 0.0216 radians. Step 5, we undertake exactly the same approach to find the angle of twist between portion CD of our shaft, this portion here. So the rearrangement to find angle CD is the same as that shown above. We do have different values now for the torque. That's positive 175 Newton meters from our torque diagram, and also the length of our shaft, portion CD here, is 0.4 meters. The G and the J are the same as above. So that evaluates to an angle of twist between portion CD of 0.011 radians. That's positive rotation. Again, considering the analogy between our shear force diagram and our torque diagram, we would have negative shear force between B and C on the diagram and positive shear force between C and D. And that's analogous here to having a negative twist between BC and a positive twist between CD. I'm not sure if the analogy helps you with your understanding, but it may help relating torque diagrams to shear diagrams. Exercise 6, solution continued. So finally, to calculate the angle of twist between portion BD of our shaft, denoted theta BD here, we simply add the angle of twist between portion BC, which was negative 0.0216 from the previous slide, to the angle of twist from portion CD, which was positive 0.011. So that evaluates to negative 0.0106 radians, and converting that into degrees, that's negative 0.607 degrees. And I'll leave you with some tutorial questions to attempt at your own pace. If you've worked through the previous exercises of this presentation, you should be able to attempt and solve these questions. In question 1 shown here, given the information in the question, we have to calculate the modulus of rigidity for the material. Remember that symbol G within our simple torsion theory. Answer is shown here in the bracket. And in question 2, we have to determine the maximum shear stress in the shaft and the angle of twist over a 1 meter length. My suggestion here, you will need to use the P is equal to T omega formula initially to find the torque applied, and using the simple torsion theory, calculate the maximum shear stress and the angle of twist. Again, answers shown in the bracket here. Question 3. This relates to a hollow section shaft, and initially we have to calculate the internal diameter, that would be lowercase d in our sketch here, of the hollow section. We're given in the question the capital D, the outside or external diameter. The suggestion here initially is to use the simple torsion theory to find the polar second area moment J, and from the standard formula for J for a hollow section shaft, we can rearrange the equation to find little d, the inside diameter or internal diameter. And the question also wants us to determine the angle of twist in degrees over a particular length of shaft. So again, we can use simple torsion theory to determine theta. The question also wants us to determine the torsional stiffness, and finally to calculate the minimum shear stress in the shaft. And here is the symbol for shear stress. I'll let you review that question at your own pace. The answers are shown in the bracket here. And finally, question 4, question 5, and again the answers are shown in the brackets. I would encourage you to start the presentation and attempt the various questions here and see if you can determine the answer stated in the questions. Be very careful with the units, make sure you are using consistent units throughout, whether that be millimetres or meters, or newtons per metre squared or newtons per millimetre squared. I wish you well with your solutions. And here's the bibliography used to help generate the presentation, and I hope this has been of interest to you, and thank you for viewing.